In this deck, we focus on the terminal concession bidding problem, where operators compete for long-term rights to develop and run major container terminals. The goal is to submit a bid that has a high probability of winning, but still makes financial and operational sense over the full concession horizon. Our setting is the Port of Valencia, which announces a 25-year concession for a new 400-meter berth container terminal, designed for about 1.5 million 20-foot equivalent units per year. Concession bidding is inherently multidimensional. Bids usually combine an upfront payment, annual lease terms, throughput and service guarantees, workforce commitments, and performance indicators. The bidder must balance aggressive promises that improve the score against the risk of overcommitting. At the same time, the Port Authority is optimizing for revenue and reliable, competitive service for shipping lines and cargo owners. This slide previews the tier structure. We begin with an integer programming formulation to define variables, objectives, and feasibility constraints. We then move to a constructive heuristic that mirrors practical scoring processes, a meta-heuristic based on ant colony optimization for multi-objective bid design, supervised learning to predict win probability, a digital twin to simulate ecosystem responses, and a human and artificial intelligence partnership to handle political and relationship-driven factors. Tier 1 frames concession award as a rigorous selection problem. Exactly one bidder is chosen, but only among bidders that meet qualification and financial feasibility requirements. The modeling value is clarity. You can explicitly represent the criteria, weights, and payment streams, and you can test how different bid structures change both port revenue and bidder profitability. This equation slide defines the sets and parameters. The set of bidders, the set of evaluation criteria, and the set of contract periods are the basic scaffolding. The weights and scores represent the evaluation system, while costs, revenue projections, and qualification thresholds translate bids into financial feasibility. In practice, these parameters are where strategy becomes explicit. This slide defines the decision variables. The key binary variable indicates which bidder is selected. A second binary variable indicates whether a bidder meets a given criterion. A continuous variable represents actual payments over contract periods. Operationally, this captures the reality that a bid is not a single number. It is a structured package of commitments spread across time. This slide presents the objective functions from two viewpoints. From the Port Authority perspective, the objective is to maximize total payments over the contract horizon. From the bidder perspective, the objective is to maximize profit, meaning projected revenue minus cost commitments. These objectives are in tension. A bid that maximizes port revenue may be too aggressive for the bidder, while a cautious bid may be profitable but less competitive. This constraint slide captures feasibility. Only one winner can be selected. Qualification constraints ensure bidders meet the minimum weighted threshold. Financial capacity constraints ensure payments do not exceed what the bidder can afford. And throughput commitment constraints ensure the port receives the minimum required operational performance. These constraints prevent a common failure mode, selecting a bid that looks great on paper but cannot be executed over the concession life. This stakeholder network figure highlights the actors and the evaluation relationships. In real concession processes, performance and credibility are judged across multiple stakeholders, not just by a single score. Use the diagram to understand why bids must address multiple dimensions. Operations, workforce, finance, and political acceptance all influence how a concession award is made. This concrete example uses 3 bidders evaluated on 4 criteria with specified weights. Under this setup, Global Port Holdings achieves the highest weighted score of 90.25. Mediterranean Terminal Company and Atlantic Container Services are both around 86 points. Because the minimum qualification threshold is 85 points, all 3 qualify. Under a pure weighted scoring mechanism, Global Port Holdings would be selected. Tier 2 introduces a constructive heuristic that mirrors how concession evaluations are often performed. First, bidders are filtered based on minimum requirements. Then, weighted scoring is computed across criteria. Finally, qualified bids are ranked, and the top score is chosen. The reported complexity is roughly proportional to the number of bidders times the number of criteria, plus a ranking step. This matters when you need transparent and auditable evaluation logic. This flow diagram summarizes the multi-stage evaluation pipeline. The key operational idea is separation of concerns. Qualification filtering prevents weak bids from consuming evaluation effort, and scoring provides a structured basis for comparison among qualified bidders. In practice, each stage can include subchecks, such as financial guarantees, technical documentation, and workforce plans. This first code section typically defines the evaluation data model. You should see a list of bidders, a list of criteria, the criterion weights, and each bidder's raw scores or commitments. It also encodes minimum requirements so the evaluation can disqualify bids that fail hard constraints before any weighted scoring is computed. This second code section usually performs the scoring and ranking. It computes the weighted score as the sum of weight times criterion score, then sorts qualified bidders. Operationally, this is where transparency matters. The algorithm should output a clear score breakdown so decision-makers can audit why one bidder outranks another. This example code sets up a realistic concession evaluation run. It defines bidder profiles and criteria, then executes the qualification filter. The practical point is reproducibility. You want a single script that rebuilds the same ranking every time from the same inputs, which is essential for governance and dispute resolution. This continuation typically runs scoring on the remaining qualified bidders, prints final scores, and produces the ranking list. In the reported example output, one bidder is disqualified for failing minimum requirements, 3 bidders remain qualified, and the winner is Global Port Holdings with a final score of 90.25. This slide shows the expected console output of the concession evaluation. One bidder, Atlantic Container, is disqualified for failing minimum requirements. 3 bidders remain qualified out of 4. The winner is Global Port Holdings with a final score of 90.25. The ranking list then shows the next best bidders, including European Maritime at 86.45 and Mediterranean Terminal Company at 86.25. Tier 3 uses ant colony optimization to search over bid design choices. Each candidate bid is treated as a path through a graph of decision points, and simulated ants build bids by choosing edges probabilistically. The algorithm reinforces good patterns through pheromones, while heuristic guidance biases the search toward cost-effective commitments. This is useful when you want to explore trade-offs between winning chances and financial exposure. This figure illustrates how ants construct bidding strategies as paths. Over iterations, pheromone trails concentrate around strong bid structures that balance score and cost. Operationally, you can interpret the converged path as a recommended bid composition, how aggressive to be on payment, throughput guarantees, and technical commitments. This equation defines the edge selection probability in anti-colony optimization. Pheromone intensity captures accumulated evidence from past good bids, while heuristic guidance represents problem-specific cost and win probability trade-offs. The alpha and beta parameters control how strongly the algorithm follows history versus heuristics, which shapes exploration and convergence. This slide defines a multi-objective structure for bidding. One objective proxy maximizes the weighted score that represents win probability. Another minimizes total bid cost. A third minimizes risk exposure from guarantees and penalties. The practical lesson is that a bid is rarely optimal on one dimension. You must manage explicit trade-offs and choose a point on the efficient frontier. This first code section typically defines the ant colony optimization decision graph. Nodes represent bid design choices, such as an upfront payment level, a throughput guarantee level, an automation package, and employment commitments. It also defines the pheromone and heuristic terms that drive selection, so the algorithm balances learned experience with problem-specific guidance like win probability versus cost. This second part usually shows how an ant constructs a full bid by choosing edges probabilistically. Once a complete bid is constructed, the algorithm evaluates it on multiple objectives. Operationally, this is where you enforce feasibility. The bid must stay within financial capacity, maintain required throughput commitments, and avoid unacceptable penalty exposure. This section typically implements pheromone update. Bids that score well deposit more pheromone, which increases the probability that future ants will reuse that structure. In a concession context, this tends to create stable patterns such as balanced financial offers combined with credible operational commitments. This final code part usually handles iteration control and convergence logging across iterations and ants. In the reported run, the optimization is described as 100 iterations with 50 ants, producing an optimal strategy that includes an upfront payment of 87.5 million euros, a throughput commitment of 1.6 million 20-foot equivalent units per year, advanced automation systems, an employment guarantee of 320 direct jobs, and a reported fitness interpreted as 78.3% win probability. This example reports an ant colony optimization run with 100 iterations and 50 ants. The recommended bid includes an upfront payment of 87.5 million euros and a throughput commitment of 1.6 million 20-foot equivalent units per year. It also includes advanced automation, an employment guarantee of 320 direct jobs, and a timeline of 22 months to operational readiness. The reported fitness is 78.3, interpreted as 78.3% win probability. Tier 4 introduces supervised learning for win probability prediction. Instead of relying only on intuition, the model learns from historical bid outcomes and competitor behavior patterns. This tier is valuable because it can quantify how changes in bid components, such as payment amount or automation level, change the estimated probability of winning. This pipeline figure shows how raw bid and market data are transformed into features, fed into predictive models, and evaluated with validation metrics. In practice, the pipeline enables scenario testing. You can adjust a bid component and immediately see how the predicted win probability and risk profile change. This code section typically defines the feature set and the model training flow. Inputs can include financial offer variables, operational commitments, technology and automation level, and competitive context. The goal is not to pick a winner automatically. It is to quantify how changing one bid component changes predicted win probability. This part usually covers model evaluation and calibration. Because win prediction is probabilistic, calibration matters. A 70% prediction should mean about 7 wins out of 10 in similar cases. You also want interpretability outputs such as feature importance so executives understand what is driving the model. This section typically implements scenario testing. You can increase upfront payment, adjust automation commitment, or change workforce guarantees and immediately see the predicted win probability shift. That is how the model becomes a negotiation tool. It helps decide which concessions are worth making. This final code part usually generates a recommended strategy profile and prints a summary. In the reported insights, financial features carry about 35% importance, competitive position about 25%, technical capabilities about 20%, risk factors about 12%, and strategic alignment about 8%. The optimized strategy is reported at 74.2% predicted win probability. This slide summarizes feature importance insights. Financial features carry about 35% importance, competitive position about 25%, technical capabilities about 20%, risk factors about 12%, and strategic alignment about 8%. The reported predicted win probability for the optimized strategy is 74.2%, showing how data-driven tuning can improve bid competitiveness. Tier 5 introduces an integrated digital twin to simulate the full concession ecosystem. It includes port authority decision logic, competitor behavior, market dynamics, operational performance, and regulatory risk. The main value is that bid decisions have ripple effects. A stronger automation commitment can increase technical score, but also changes cost, risk, and competitor responses. This architecture figure shows the main modules of the digital twin and how they exchange information. The model captures how evaluation criteria, competitor behavior, and operational reality interact. This lets decision-makers run what-if experiments and stress tests before finalizing a bid package. This first code section typically defines the simulation state: bidder profiles, competitor response rules, port authority scoring logic, and market assumptions. Operationally, a digital twin here means you can run thousands of bid variants and see not only your score, but how competitors might react. This part usually implements competitor behavior simulation. Competitors can adjust their own automation commitments or pricing after observing your bid strength. That reaction model is crucial because in real concessions, you are rarely competing against static rivals. This section typically computes outcome metrics, such as predicted win probability, expected profitability, and risk exposure under many simulated worlds. It also records scenario traces so you can explain why a bid is preferred, not just that it is preferred. This final code part usually summarizes the best performing bid variants and performs sensitivity analysis. In the reported interoperability example, increasing automation investment from 45 million euros to 65 million euros raises predicted win probability from 68.3% to 72.8% and improves expected net present value by 28.8 million euros, while shifting risk from operations toward technology obsolescence. This example quantifies how bid changes propagate. Increasing automation investment from 45 million euros to 65 million euros increases predicted win probability from 68.3% to 72.8%. It also improves expected net present value by 28.8 million euros due to productivity gains, while shifting risk from operations toward technology obsolescence. The twin also predicts competitors will adapt by increasing their own technology commitments. Tier 7 introduces a human and artificial intelligence partnership for concession bidding. Artificial intelligence excels at processing data, competitor intelligence, and scenario modeling. Humans contribute political nuance, cultural context, and relationship-driven negotiation strategy. The goal is a bid that is not only numerically optimized, but also feasible and credible in the real decision environment. This figure illustrates the human and artificial intelligence collaboration architecture. An explainable interface is central because decision-makers must understand and trust why a bid recommendation is preferred. The architecture also emphasizes iteration. Humans provide feedback, and the model updates the search and the scenario set accordingly. This first code section typically defines how human constraints enter the system. Humans can add hard constraints like workforce commitments or political feasibility rules that override purely financial optimization. It also defines how the system records human rationale so that future recommendations do not repeat the same strategic mistake. This part usually implements the iterative loop. AI proposes bid variants, humans adjust priorities and add context, and the system re-optimizes. Operationally, this prevents paper-optimal bids that are politically infeasible or culturally tone-deaf. This final code segment typically outputs the recommended bid S plus an explanation package, why it wins, what trade-offs it makes, and what risks it carries. In the Thessaloniki example, humans add 50 additional job commitments and a 2 million euros annual community fund. The symbiotic outcome reaches 76.4% win probability, compared with 68.3% for AI only and 59.7% for human only, with expected net present value of 298.7 million euros and political risk score 18 out of 100. This example describes a concession in Thessaloniki where human inputs change the recommended bid. Humans add a commitment of 50 additional jobs and a 2 million euros annual community fund to improve political acceptance. The symbiotic approach achieves a 76.4% win probability, compared with 68.3% for artificial intelligence only and 59.7% for human only. It reports expected net present value of 298.7 million euros and a political risk score of 18 out of 100. These practice questions emphasize implementation readiness. You practice building an integer programming selection model, implementing qualification filtering and ranking heuristics, and designing anti-colony optimization for multi-objective bid design. You also practice building a supervised learning pipeline, designing a digital twin simulation architecture, and structuring a human and artificial intelligence workflow for high political risk concession environments. To close, terminal concession bidding is a multi-objective strategic problem. Winning depends on balancing financial commitments, operational credibility, and risk. while aligning with port authority priorities. Integer programming provides a rigorous foundation. Heuristics and meta-heuristics explore bid design trade-offs. Machine learning quantifies win probability drivers, and digital twins and human and artificial intelligence partnerships handle the full ecosystem reality.